Hi everyone! In this video I'm going to present our linear mechanical reduction system. The goal of this project was to create a mechanism that reduces displacement in a precise and controlled way. We designed and built a prototype to test its performance and see how well it works. I'll briefly explain how it works, the main challenges we faced, and what we learned from the experiment. The objective is to design and thoroughly test a displacement demultiplication mechanism, ensuring high performance and reliability. The key focus areas include precise and accurate realization of the demultiplication factor. The mechanism must achieve a demultiplication factor of 20 with minimal deviation, ensuring consistent and repeatable performance. Linearity of output motion. The system should exhibit a highly linear response, minimizing nonlinear distortions to maintain predictable and controlled displacement behavior. Conformity to the test environment. The mechanism must be designed to operate efficiently under the specified test conditions, taking into account factors such as temperature variations, vibrations, and spatial constraints. Originality of the solution. The approach should introduce innovative design elements or optimizations that enhance performance, reliability, or efficiency compared to existing solutions. This study aims to develop a robust and efficient mechanism that meets stringent accuracy and performance criteria, ensuring its applicability in practical engineering contexts. The House of Quality (QFD) is a methodology used to analyze and structure product requirements comprehensively. It serves as a set of metrics that define product characteristics clearly. The designed system must meet fundamental requirements to ensure optimal performance. It should exhibit a linear response, ensuring predictable and uniform input-output behavior. Repeatability is essential, allowing the system to deliver identical results under the same conditions. The system also requires high accuracy and reliability, ensuring precise and consistent measurements that closely align with the reference values. Additionally, it should maintain stability despite temperature fluctuations and be equipped with standardized attachments to ensure compatibility with existing equipment. The system is designed to meet the following specifications. The number of components must be low, and the planar dimensions need to be limited. The temperature range must ensure operational stability across varying conditions. We also need the system to be linear, with output dimensions big enough to ensure a correct measurement of the displacement. Also, the demultiplication factor should meet the one defined at the beginning. There are also some specifications relative to the correct positioning of the Kelvin clamp, to the distance between line of action and line of measurement, and about the maximum allowable displacement. We've developed 5 different concepts, each time increasing the complexity and creativity behind their design. Some concepts were found to be unsuitable due to the input-output relationship. Others exceeded the size constraints, and some didn't meet the imposed force limitations. The following slides present the 5 generated concepts, each accompanied by a short video and a brief description. This concept is the double compound linear spring, and it was inspired by an example presented during class. It presented numerous issues, the most significant being the failure to achieve the desired input-output ratio, delivering only an half instead of the target 1/20. However, we included this concept as it will be used later to linearize the input and the output of other concepts. With the second concept, we introduced a greater reduction in output displacement, though it still didn't meet the required specifications. Achieving the specified ratio was possible only by increasing the lever system on the left parallel bit, which, however, compromised the maximum allowable system dimensions. This concept utilizes a double compound mechanism to linearize both input and output. Thanks to this component, we achieved excellent output linearity that meets the given specifications, as shown in the next slide. Additionally, the central lever provides a 5-fold input reduction, resulting in an overall 20-fold input reduction as required. The maximum size constraints is also respected. However, the main issue remains the stiffness, which is too high for the applied forces. This concept leverages a completely different lever principle compared to the previous ones. With this design, we significantly simplified the prior concepts by reducing the number of joints and ensuring a more straightforward operation. However, we faced considerable challenges in finding a suitable configuration, as only a few setups complied with the imposed constraints. Another issue is the output linearity, which is not guaranteed and may result in a potential plate inclination. The final concept combines the fourth and the first designs. This combination ensures an almost perfectly linear output, while meeting all the other given specifications. During the concept selection phase, we discarded inadequate concepts, retaining only those that met the required technical specifications. Concepts 3, 4, and 5 satisfied the criteria of linearity, dimensional constraints, positioning of input and output plates, and displacement ratio of 1/20. The final choice was Concept 5, due to the following advantages: functional simplicity, fewer notches, input force compatible with the given specifications, and a reduced number of cuts during EDM machining. We therefore proceeded with a more detailed study of Concept 5. The MATLAB simulations made it possible to identify the optimal element dimensions required to achieve the desired reduction ratio. Based on these parameters, a 3D model was developed as the basis for cutting the available plates. One key design consideration was how to represent flexures. In the MATLAB simulations, the flexures were simplified as point elements. However, in the real system, flexures have a measurable thickness, finite dimensions, and a developed structure. To reconcile this difference, the centers of the actual flexures were carefully aligned with the corresponding points used in the MATLAB model. This approach ensured that, despite the physical size and shape of the flexures, the real mechanism behaves in a manner consistent with the simulation. The primary mechanism provides a reduction factor of 10. Additionally, a double compound system was added at the output, in order to direct the motion along a single desired direction, and doubling the reduction factor, achieving an overall reduction ratio of 20. On a second plate, a dedicated attachment for the measurement system was fabricated, along with the necessary holes to connect it to the first plate using screws. The contact between the two plates helps to minimize deflection caused by the weight of the mechanism, and friction-related issues on the plates were mitigated through the use of a lubricant. The mechanism was subjected to a stress and displacement simulation using Autodesk Inventor. The analysis was performed by first applying constraints near the V-grooves, imposing an absolute fixing constraints to simulate the Kelvin clamp. Additionally, collinear constraints were assigned to the holes of the screws that fastened the two plates together. Along with the constraints, a concentrated force was applied to the input plate. Furthermore, specific points of interest were defined, for which the displacement relative to their initial or resting position was subsequently evaluated. The EDM machining of the piece was performed in the PROM facility at Rovereto. To avoid the decutted pieces falling down and possibly harming the process, we applied some magnets between the separating parts. These magnets had to be removed between different cuts, being extremely careful not to harm the product. Before extracting the finished piece from the remaining structure, we fixed it to its base with 4 bolts. We could then remove the magnets and the waste metal to obtain our finished product ready to be tested in the university laboratory. The laboratory testing was performed using the following setup. The mechanism was mounted on a Kelvin clamp between a manual input displacement actuator and a laser output displacement sensor. The effect of the input actuator was also measured with another laser displacement sensor, placed behind the overall system. The testing was done in standard laboratory conditions, with 3 different test modes: a continuous input displacement to analyze the dynamic response, a stepped input displacement to get a static characterization, and one with no input displacement to evaluate the background noise. For each test mode, 3 different tests were performed. Here we can see the results from a continuous test. The graph shows a significant amount of hysteresis, but most of it is due to the intended movement of the mechanism caused by the incorrectly machined V-groove. This makes it difficult to isolate and evaluate the intrinsic hysteresis of the mechanism itself. Another important observation is the slope of the curve. Ideally, the forward and return paths should have the same slope. However, in our case, the slope during the forward motion is about half of what it should be. This is because the input force, combined with the elastic force of the system, caused an unintended displacement of the mechanism, affecting the expected behavior. This graph shows the results from a step test. Similar to the previous case, we can observe significant hysteresis due to the mechanism shifting inside the faulty V-groove. This makes it difficult to extract precise conclusions about the system's behavior. Additionally, we encountered issues with the laser losing focus during several tests, making most of the data difficult to interpret. The results shown here are the most readable ones, but they still reflect the influence of alignment errors, rather than the pure mechanical response of the system. Overall, these tests highlight the main limitations of our setup, and suggest that improvements in mechanical alignment and laser positioning will be necessary for more reliable measurements. In conclusion, our linear mechanical reduction system demonstrated promising behavior, but several issues emerged during testing. First, we observed a significant problem related to environmental vibrations. When 5 people were standing close to the experiment, their mere presence influenced the measurements, indicating a sensitivity to external disturbances. Additionally, the presence of people affected the ambient temperature and humidity, leading to unpredictable thermal expansions in the mechanism. This effect was further exacerbated by the non-kinematic design, making the system more susceptible to dimensional changes. Second, the V-groove wasn't machined correctly, leading to an intended movement with minimal force. This introduced an apparent hysteresis in the system. Additionally, the slight misalignment caused the mechanism to sit above the laser measurement plane. As a result, the laser beam hit a small mirror attached to the output, making the measurement highly dependent on the mirror's alignment. This misalignment likely contributed to another issue. The laser frequently went out of focus, further affecting the accuracy and consistency of the measurements. Finally, the design was not fully kinematic or isostatic. As mentioned, this made it sensitive to thermal expansions, which could introduce unpredictable deformations and compromise measurement accuracy. Despite these challenges, the experiment provided valuable insights into the system's behavior and highlighted key areas for improvement in future iterations.